Hello children, in today's class we will be discussing about electromagnetic induction and a related Faraday's experiment. Children, this topic is a part of Electromagnetism Unit C. Then you may get a wonder, sir, what about Unit A and Unit B? Yes, children, Unit A and Unit B already were uploaded in our channel. Links will be given in the description. Just kindly go through those videos. Children, in a Unit A and Unit B, only one point was there. What was that actually? Magnetic effects of current. So, Unit C, it's a completely reverse we are going to discuss. Is that clear? So, links will be given in the description. Kindly go through this video. So, in today's video, only single point is there. What is that? Electromagnetic induction. So, children, in order to understand the electromagnetic induction, we need to understand about one more physical quantity, which is a very important, and textbook it is not highlighted that much actually. But we have to get a command on that physical quantity. Then what will happen, the concept so-called electromagnetic induction will become very, very easy. So what is that physical quantity, children? Yes, that is magnetic flux. First, we need to understand magnetic flux. Then automatically what will happen, we get the grip on electromagnetic induction. Children, first let us try to understand what is a magnetic flux. Children, for that, let us consider the magnetic field around the bar magnet. So we all know very well the pattern of the magnetic field around the bar magnet, how it will be. So it looks like this two-dimensional. Of course, so magnetic field will be there around the magnet, but it is just we have taken as a two-dimensional view of the magnetic field produced by the bar magnet. Children, here we consider the two surface areas. This one, first one, surface area 1, and this is surface area 2. But how these two surface areas, not like this. They are not in the plane of the board. Rather, they are perpendicular like this. So that field lines are passing like this. Try to understand. Field lines are passing like this. So through this A1, field lines are passing like this. And through A2 also, field lines are passing. So what I mean to say that this is a normal. Try to understand. So field lines are passing normal to the surface. They are perpendicularly. So field lines are passing perpendicular to the surface areas which we considered. And children, now I can say that the magnetic flux linked with A2 is, let us say, see, magnetic flux will show with the letter pi, and the magnetic flux linked with this A2, I can say it is a pi 2, and the magnetic flux linked with A1 is a pi 1. Then I can conclude that here pi 2 is greater than pi 1. I can conclude that pi 2 is greater than pi 1. Then you may get a one doubt. Sir, first of all, you did not say what is the magnetic flux. Then how can you say that pi 2 is greater than pi 1? Yes, coming to that point only, children. Now try to observe this surface area A2 and A1. You will understand. What difference do you notice, children? What difference do you notice? Yes, you are right. So through A2, more number of field lines are passing. Okay, yes. Through A1, less number of field lines are passing. So what is a magnetic flux? Means here, which one is deciding the magnetic flux, children? The number of field lines which are passing through certain area deciding the magnitude of the magnetic flux. So first, how to define the magnetic flux, children? The number of field lines which are passing per unit area normal to that surface. So I repeat once again, the number of magnetic field lines which are passing through a certain area means normal to that area. I repeat once again, like it's very, 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 very important. The number of magnetic field lines which are passing per unit normal area is called magnetic flux. So here more number of field lines are passing, so magnetic flux is more. Here less number of field lines are passing, so magnetic flux is less. Is that clear? Yes. And here one more important thing, children. The cbse unit of magnetic flux is Weber. Children, Weber. I repeat what is very, very, very important. Weber. Why it is important, So in order to understand the units of the magnetic field, Weber per meter square. From where that Weber is coming? Yes, from here only it is coming. Okay, fine. And so it is not a CGS, it is a SI system, SI unit it is. Then what is the CGS unit of the magnetic flux? It is a Maxwell. It is a Maxwell. Don't get confused. These all are the scientist names only. Okay. Then how Weber and Maxwell are related, children? So here 1 Weber is equal to 10 power 8 Maxwell. 10 power 8 Maxwell. 10 power 8 Maxwell. So it is a relation. Children, what is the magnetic flux? What is the magnetic flux? What is the magnetic flux, children? It's very important. The number of magnetic field lines which are passing per unit normal area is called magnetic flux. So more the number of field lines, more the magnetic flux, less the number of field lines, less the magnetic flux. And the S unit of magnetic flux is Weber and the CGS unit of magnetic flux is Maxwell. 1 Weber is equal to 10 power 8 Maxwell. Is it clear? Fine. Now, we discuss about electromagnetic induction. So, in order to understand the electromagnetic induction, children, so we need to just look into the experimental setup made by the Faraday. First of all, why he got that idea, okay, and how it will be, and what we can say. Okay, children, is that clear? Can I raise 3, 2, 1, go? Yes. Now, first we will see the arrangement setup, what we get the circuit which is made by the Faraday. Let us see. Then we will slowly discuss what is the electromagnetic induction and the related very important points and Faraday experiment and the conclusions, on which factor does the induced EMF, so-called current, depend. So, examination point of its conclusions of Faraday experiments are very important. So, look at here. First, let us take a circuit here. It is moved away from the coil. Okay, look at here. So, for this a simple experimental setup he made. First of all, how did he get this thought to his mind actually? Children, already we learned about the Oersted experiment. So, what was the main point behind the Oersted experiment, children? Yes, he proved that current carrying conductor produces magnetic field, which means what? With electric current, with electrical energy, we can produce magnetic field. With electric current, we can produce magnetic field actually. Then here, Faraday, he got an idea. As we are producing what we current to magnetic field, why can't we produce the current from the magnetic field? So, it's a completely opposite phenomenon. Children, I repeat once. In an Oersted experiment, it was proved that magnetic field is produced by the electric current, by the electrical energy. Then he got doubt, then why can't we produce electrical energy by the magnetic field? So, as a result only, today all what we can say generators are working and we are enjoying the electrical energy. First, children, what is the experimental setup by the Faraday, let us say? First, children, for that he has taken a copper coil and a bar magnet. Simple it is, you also can do it, we all can, it's a simple experiment. Okay, so copper coil and a bar magnet. Just try to understand. So, in this copper coil, only galvanometer is connected. Here is only galvanometer is connected. Children, what is the purpose of galvanometer? Even small amounts of currents are there in the circuit also, it will show the deflections. Try to understand. Very, very, very small amounts, even which can't be measured by an what we can say ammeter also. This will show deflections. This it's like a tester. If current is flowing, it will show deflection. If a current direction is reversed, what happens? Deflection will be reversed. For example, if a current is flowing clockwise, example I am telling clockwise, if it is showing right side deflection, if a current direction is reversed, then it will show what? It will show opposite direction. Means not only presence of current, it also will give you the direction of current also. But provided that there must be some current. If not, galvanometer does not show any deflection. Children, just look at these two circuits here and here. So, do you think that in these two cases galvanometer will show deflection? No, definitely, because there is no source of electrical energy. But what actually Faraday noticed, when this bar magnet is moved, okay, let us say, see, when bar magnet is moved means either with the north pole or south pole you have to move it, right? So, what happened, when this north pole of the bar magnet is moved towards the coil, what happened, he could find some deflections in a galvanometer, surprisingly, right? So, when it is moved towards the coil, so he noticed that, some current is set up, so that it is showing deflections, let us say right side, just for a assumption I am taking, okay, fine. And what happened, when this bar magnet is taken away from the coil, it also noticed that this pointer of the galvanometer is deflecting in the opposite direction, which means what here? Current direction might be reversed. Current direction might be reversed. But so let me tell you how the coil means. The coil is not in the paper, in the plane of this one. So here, let me take this charger once. Okay, let me just try, let us try to make like a coil. Okay, children, let us say it's like a coil. Try to understand. Here is a coil. Here is a coil. Okay, it's coil. So it is not like this actually. It is like this coil. So let us think it is a bar magnet. So when this bar magnet is pushed towards the coil, yes, we can find the deflections. Even it is taken away from the coil, still we can find the deflections. But children, again let me tell you, in the first case what he did, let me tell you clearly. First, he kept coil at rest, then with the north pole of the bar magnet, it is pushed, the north pole of the bar magnet is pushed towards the coil. Then deflections were found, which means what? Current is flowing. If it is taken again away from the coil, same north pole is taken away from the coil, the deflections are shown in opposite direction, which means what? Current is reversed. Even you can do with the same with the south pole also. Okay, it's the first case where the coil is at rest, magnet is in motion. Now second case, let us say, yes, bar magnet is at rest. Now coil is moved towards this one. Okay, then still deflections are found. Even it is taken away from this bar magnet also, deflections are found. Case 2, where magnet is at rest, coil is in motion. Case 3, if both are in motion like this both are pushed together like this, or both are taken away from this. But children, here one surprising thing is found actually. Okay, it's very happy that yes, as a galvanometer showing deflection means yes, current is produced. It's okay. But it's a coil. As it is moving, deflection is there. The moment when it is stopped, there is no deflection. Try to understand. Means as long as there is a motion, so-called relative motion between a bar magnet and a coil, if both are placed very close to each other, no. The moment when it is pushed and the moment when it is taken, means there must be some relative motion. So clearly it was noticed that as long as there is a relative motion between the coil and bar magnet, what is happening? Some electromotive force is induced, which results induced current. So this phenomena only we can call it as a electromagnetic induction. What is electromagnetic induction, children? I repeat once again. So when there is a relative motion between, the, what we can say, relative motion between the coil and the magnetic field, induced EMF is produced, which leads to induced current. This phenomena is called electromagnetic induction. So children, what are the conclusions? I repeat once. What are the conclusions? First, what is the first conclusion, children? So there must be a relative motion. Children, I repeat once again. There must be a relative motion. So if there is no relative motion, if both are at rest, then there is no current. So there must be a relative motion between the coil and magnet. Means either of one is motion, it's okay. If both are in motion, it's okay. But both should not be at rest. That is the first one. What is the first one, children? There must be a relative motion between the coil and the magnet. And what is the second one? If you can move faster manner, either this magnet or a coil, you can find that the deflections are in a faster manner, which means what here? More current is produced. Is it clear? So these are the conclusions. But here we will get one doubt. Sir, we are moving a magnet, we are moving a coil. But what is happening? Yes, Dechal, we are coming to that point only. So to understand this only, we need a concept of magnetic flux. That's what we discussed first only. Children, what is a magnetic flux? What is a magnetic flux? So here, magnetic flux, children, I repeat once again. What is a magnetic? Okay, let me draw from this side. What is a magnetic flux? The number of magnetic field lines which are passing through a certain area, or simply we can say the number of field lines which are passing per unit normal area is called magnetic flux. And here, if the more number of field lines are passing, more is the magnetic flux. If a less number of field lines are passing, the magnetic flux is less. Okay, fine. Let us say here is a north pole and a south pole. Children, let us say this coil is at rest. Coil is at rest, let us say that. Now as we are bringing this magnet towards the coil, taking away from the coil, towards the coil, away from the coil. But here what is happening, children? Yes, don't forget that around the bar magnet, what will be there? Magnetic field lines will be there, right? How the magnetic field lines? Yes, so magnetic field lines will be like this. Are you able to see? I'm trying to show the red color. I think it is not. It is not working, children. Okay, let me try. So here magnetic field lines. So this is how magnetic field lines are able to. This color is writing very light. Let me check. Okay, type. Okay. Let me also add then black color. So magnetic field lines. Magnetic field lines. Let us say. So this is how magnetic field lines will be there, which are passing. Now children, try to understand. Now it is a magnet. Children, it is a magnet. Now as I am bringing this magnet towards the coil, what will happen, children? Yes, the number of field lines which are passing through the coil increases. Means what? There is a magnetic flux. Try to understand. So slowly I am bringing this magnet towards the coil. Then what is happening? The number of field lines which are passing through the coil increasing. Okay. Then if I am taking this magnet away from the coil, then what is happening? The number of field lines which are passing through the coil are decreasing. Children, already we learned. What is that? The number of field lines which are passing through a certain area is called what? Magnetic flux. So during this process, as we are bringing towards the coil, taking away from the coil, towards the coil, away from the coil, what is happening? The magnetic flux linked with the coil is changing. Let us say when it is here, two field lines are passing. As I am taking 3, 4, 5, 6, 7, 8, 9, means the number of field lines which are passing through the coil increasing. If I am taking this away, 10, 9, 8, okay, 7, 6, 5, 4, means the number of field lines which are passing through the coil decreasing. So which means what, children? There is a change in magnetic flux linked with the coil. There is a change in magnetic flux linked with the coil. So there will be a change in magnetic flux linked with the coil. So this change in magnetic flux linked with the coil is responsible for the production of EMF, so called induced EMF, which causes induced current. Children, so as we are moving this bar magnet towards the coil and away from the coil, what is happening? There is a change in magnetic flux. There is a magnetic flux linked with the coil is changed. The magnetic flux linked with the coil is changed. Then only what is happening? Current is produced. Children, this is the main point behind the generation of AC current. So when we are learning about the AC generator, this point is a very important. Is it clear? Fine. So this is what I repeat once again here. So during this process, what is happening? There is a change in magnetic flux linked with the coil. The magnetic flux linked with the coil is changing continuously. So as long as there is a change in a magnetic flux linked with the coil, then only current will be there. Children, let us just try to just see the conclusions of Faraday experiment. Children, the first one is that as long as there is a relative motion, very important term this is. So there is a relative motion between bar magnet and a coil, there will be a induced current. The moment when the motion is stopped, the current is stopped. Okay, fine. And the second one, children, direction of current, very important. The direction of current induced depends on the polarity, If you can change the polarity, and the direction of current also reversed. Okay, fine. And now here, the magnitude of the current produced in the coil, children, the current produced in the coil depends on mainly four factors. First one is what? It depends on rapid motion. Either you can move bar magnet towards the coil or coil towards the bar magnet, or two you can. if the motion is increased, then obviously what will happen? The flux linked with the coil also increases, which causes more current in the coil. Okay, fine. And second one, so you can increase the current in the coil by using a strong magnet. Yes, you can strong magnet by using strong. So strong magnet in the sense what, children? More number of field lines will be there. Obviously, there is a more chance to pass more magnetic flux field lines through a coil. So obviously, more flux will be there, and there will be change in the magnetic flux linked to the coil also will become more. Okay, fine. And the third one, number of turns of the coil. Number of turns of the coil. So children, here, if the more number of turns are there, obviously more magnetic field lines will pass, more magnetic flux, more change in magnetic flux, more induced current. And the last one is that surface area of the coil. Surface area of the coil. Yes, obviously children. So as the surface area is more, obviously, so more number of field lines will pass, which causes more change in magnetic flux. As a result, we will get the more current. Okay, na? So these are the conclusions, and these are the current produced, induced current I can say. It's not current, induced current. Okay, now produced in the coil depends on these 4 factors. Can I do this? Fine. So examination point of view, these Faraday's laws of electromagnetic induction are very important. Just we have only 2 children. The first one, so Faraday's, let me write here. So Faraday's laws of electromagnetic induction. So what is the first one, children? Yes, so there must be some magnetic flux linked with the coil should change. Again, I am telling you. So there must be a magnetic flux, children. So whenever there is a magnetic flux linked with the coil is changed, there is a induced EMF. Means what here? There must be a change in magnetic flux linked with the coil always. Then only what will happen? There will be production of induced current. I repeat once again. So there must be some magnetic flux linked with the coil should change. In simple terms, magnetic flux linked with the coil should change continuously. Then only there will be a induced current. And the second thing is that, children, yes, this change in magnetic flux, I can repeat once again. So which is producing EMF, that EMF produced, children, induced EMF produced, is directly proportional to the rate of change of magnetic flux. At what rate? If this rate of change of magnetic flux is more linked with the coil, then induced EMF will be more. Okay, na? So here only we can write EMF is equal to N into constant d pi by dt. What is N here? N is the number of turns of the coil. Here we are placing a minus. So why are we placing a minus? That we will discuss in the next class. The importance of minus is there actually. That we will discuss in next class. Okay, so these are the 2 Faraday's laws of electromagnetic induction. Is it clear, children? So what, see, single point, children, it is opposite to the Oersted experiment. Oersted proved that we can produce a magnetic field with the help of current. But here Faraday proved that we can produce a current with the help of what? Change in magnetic field. Is it clear, children? Fine. So this is all about the today's class. In the next class we discussed, today's class we discussed current, how the induced current is produced. So next class we discuss how to find the direction of induced current in the coil and as well as in a linear conductors. Okay, children, thank you so much. All the very best.